Good morning. Today I can understand how sample size affects the mean and standard deviation in a sample distribution by finding the confidence intervals. There's actually a lot of different little components to this lesson, but basically we're going to be talking about what a sample distribution is and different things that come of it. So here's what a sample distribution is. Let's say that I want to flip a coin and I want to determine the proportion that lands on heads. So let's kind of like simulate that here. In fact, let me just pause for a moment. All right, so we're going to flip the, why not, it's National Women's Month, so let's Women's History Month. Let's do the Susan B. Anthony coin. So I'm going to flip it 5 times, and I'm going to record the proportion of heads. So that's 1 out of 1, 1 out of 2, 2 out of 3, 3 out of 4, 3 out of 5. So if I put this on what we call a sample distribution, we got 3 out of 5, which is 0.6. So if I make this, let me just do that a little bit smaller. Now we'll do it big. And if I did 0.0, 0.1, 0.2, 0.3, 0.4, 0.5, 0.6, 0.7, 0.8, 0.9, and then 1.0. So I would put a little X above the 0.6 because that represents that that's what I got. Now I'm going to do that again. So 1 out of 1, 1 out of 2, 2 out of 3, 3 out of 4, 3 out of 5. All right, I got another 0.6. And let's do another one. 1 out of 1, 2 out of 2, 3 out of 3, 3 out of 4, 3 out of 5. I got another 0.6. Well, this is working out very interestingly. And if I go again, I've got 0 out of 1, 1 out of 2, 1 out of 3, 1 out of 4, 2 out of 5. I got a 0.4. All right, I don't know why I keep hitting the calculator. All right, let's go again. 1 out of 1, 1 out of 2, 1 out of 3, 2 out of 4, 2 out of 5. Now, what we'd normally do in class is each group, I would move you guys into pairs, and each pair would keep on flipping. So you can kind of do this on your own right now. Get the coin and flip it and see what you end up getting. It's 0 out of 1, 0 out of 2, 1 out of 3, 2 out of 4, 2 out of 5. And let's keep on going. 1 out of 1, 1 out of 2, 2 out of 3, 3 out of 4, 4 out of 5. So we got a 0.8. Now, if I keep on going, I'm going to get what this would most likely look like. I'm going to get mostly 0.4s and 0.6s. I'm going to get a couple of 0.8s and 0.2s. And then I might get like maybe 1 of 5 heads and maybe 1 of no heads. So my sample distribution would look something like this. Now this should look a little familiar to you. This looks like the normal distribution curve. And that's what it would look like approximately with a sample size of 5, meaning I flipped the coin 5 times. So now what I'm going to do is I'm going to put that together. And what I'm going to do, I'm just going to hide this for a little bit. Just move it to a different page. And now I'm going to do it again. But instead of a sample size of 5, I'm going to do a sample size of 20. Now, in class, I would probably do I would do a sample size of 10 next and then 20. But, hopefully I'm not boring you too much yet. It's a little bit better when it's a little bit more interactive. But again, I encourage you to kind of flip a coin on your own as we're doing this. So now I'm going to flip a coin 20 times and record the percentage, the probability of it landing on heads. So I've got 1 out of 1, 1 out of 2, 2 out of 3, 3 out of 4, 4 out of 5, 5 out of 6, 5 out of 7, 5 out of 8, 5 out of 9, 5 out of 10, 6 out of 11, 7 out of 12, 8 out of 13, 9 out of 14, 9 out of 15, 10 out of 16, 11 out of 17, 11 out of 18, 12 out of 19, 12 out of 20, 12 out of 20 is 0.6. Now, I want you to think about this for a second. My first 5 flips, I had 4 out of 5 of them land on heads, which is 0.8. So if I was doing a sample size of 5, I would have gotten 0.8. And then I think out of my next 5, I think it was like 20% were heads. So that would have been a 0.2. But that 0.8 and 0.2 didn't happen because I increased the sample size. When I increased the sample size, those things kind of balance themselves out. So I ended up with a 0.6. And what the point is going to be, it's going to be very hard to get something that's not near the middle. Let's do it a couple more times. And again, I encourage you to do this on your own as well. 1 out of 1, 2 out of 2, 3 out of 3, 4 out of 4, 5 out of 5. So if I was doing a sample size of 5, I would have a 1.0 on my distribution. I'm not doing a sample size of 5, but if I did, I would have a 1.0 all the way at the end right now. So I'm 5 out of 5 so far. 6 out of 6. 7 out of 7. This is insane. 7 out of 8. 7 out of 9. 8 out of 10. 8 out of 11. 8 out of 12. 8 out of 13. 9 out of 14. 9 out of 15. 10 out of 16. 10 out of 17. 10 out of 18, 11 out of 19, 12 out of 20. It's again 0.6. So I started off way out here at 1.0 after 5 flips. After 10 flips, I was at 0.8. But because the sample size increased, because I flipped the coin so many more times, it ended up back closer to the middle. Let's do one more. I don't know why I keep on going to that calculator. 1 out of 1, 1 out of 2, 2 out of 3, 2 out of 4, 2 out of 5, 3 out of 6, 3 out of 7, 3 out of 8, 3 out of 9, 3 out of 10. So keep in mind, this is a sample size of 10. That would be at 0.3. But I'm not a sample size of 10. I'm 3 out of 10 so far. 3 out of 11, 3 out of 12, 3 out of 13, 4 out of 14, 4 out of 15, 5 out of 16, 5 out of 17, 5 out of 18, 5 out of 19, 6 out of 20. .3. Now, even though 0.3 is pretty far from the middle, we were at 0.8 for a while early on. So here's what's going to end up happening. I'm going to get most of mine around here. and maybe I get something like this. I'm not going to get these 0.0s and 0.1s and 0.9s and 0.10s because, like, if I flip the coin 5 times, it's not that impossible for it to come up heads 5 times in a row. But to flip it 20 times and get heads 20 times in a row is a lot less unlikely. To flip it 50 times, 100 times, it's a lot less unlikely. So what I end up with, it's still my normal distribution curve, but we're going to compare this with the one that we just did. So this one has a sample size of 20, meaning I flipped the coin 20 times. So we're going to compare this to the sample size of 5. Come on, where are you? Where'd it go? Oh no, I lost it. There it is. I don't know what happened, but it's back. Just copy it this time, so don't have to worry about losing it. There we go. So let's make it a little bit smaller. So let's compare these two. Let's talk about what's the same about them. Let's talk about what's different about them. What's the same about them is that they are both centered around the middle, meaning that their mean is relatively the same. So as I increase sample size, as we increase sample size, 1, the mean relatively stays the same. And it's going to stay very close to 0.5 because the empirical probability, empirical means what actually happens, the theoretical probability, that's what should happen is of getting heads is 1 out of 2, which is 0.5. So the mean flipping a coin is going to relatively stay the same as I increase sample size. It's going to be very close to 0.5. Now, the standard deviation or the spread. You see how the top one spreads out to 0 and to 1.0, but this one spreads to 0.2 and to 0.8. The spread or variability decreases. Everything gets tighter to the mean. Doesn't have as great of a range. The spread / variability / standard deviation decreases. Everything gets closer to the mean. If I were to do a sample size of 1,000, it would probably look something like this, where probably even tighter than this, where again the mean is still relatively the same. This would be let's say sample size. This would probably be more like a sample size of like 100. Where the mean is still relatively the same, the mean is still relatively close to 0.5, But the spread, the variability, how far it extends out is going to be even tighter to the mean. So what you should get from everything that we just did, as we increase sample size, the mean relatively stays the same. The spread or variability or standard deviation, they all kind of mean the same thing, will decrease. All the data will get closer to the mean. You're not going to have these 1.0s and 0.0s because if I flip the coin 5 times, there's a 1 out of 32 chance I'm going to get 0.0. If I flip the coin 20 times, it's 1 out of 2 to the 20th power. It's 1 out of 1,048,576. So listen, if I did this experiment 1,048,576 times, I'm probably going to get 1.0. If I flip it, if my sample size is 5, I'm going to probably get it quite a lot of times if I flip it a million times. So that's the big thing to take from this. Let's take a look at some examples based on this, some questions that are based on this. We're going to also talk about some other stuff as well as we go through. So again, before we move on, this is what you're supposed to get out of this whole thing. As we increase sample size, meaning we go from 5 flips of the coin to 10 flips of the coin to 20 to 100 to 1,000 to 1,000,000, the mean will relatively stay the same. It'll stay close to 0.5. And the spread or variability or standard deviation will decrease, meaning that all the values will get closer to the mean. You're not going to have as large of a spread. You're not going to have the numbers out on the outside of the curve. These are going to be empty or have very, very, very few. A group of 11th graders wanted to estimate the population proportion of students in their high school who drink at least 1 soda per day. Each student selected a different random sample of 30 students and calculated the proportion that drink at least 1 soda per day. The dot plot below shows the sampling distribution. The distribution has a mean of 0.51 and a standard deviation of 0.09. So just so you understand what's happening here, each of these dots, let's say I take a look at this dot right here. This means that somebody asked 30 students, and out of those 30 students, 50% of them, or 15 out of 30, drank at least 1 soda per day. This dot means that somebody asked 30 students and 30% of them, so I guess that would be 10 out of 30, drank at least 1 can of soda per day. So that's what each of these dots means. So I just want to make sure we understand what we're looking at here. So, find the margin of error and the confidence interval. Explain the meaning of the confidence interval in the context of the problem. So, we've talked about confidence interval in an earlier lesson, and it's going to come up a lot here. And the confidence interval is the mean plus and minus 2 times the standard deviation. Margin of error, we haven't talked about yet, but margin of error is what you're adding and subtracting to the mean to get the confidence interval. It's just 2 times the standard deviation. So the confidence interval is the mean plus and minus 2 times the standard deviation. The confidence interval is, it says the mean is 0.51 plus 2 times 0.09 and 0.51 minus 2 times 0.09. So let's go to our calculator and let's do 0.51 plus 2 times 0.09. And let's do 0.51 minus 2.09, 0.69, 0.33. So the confidence interval is 0.33 to 0.69. The margin of error is just 2 times the standard deviation. Which is 2 times 0.09, which is 0.18. So Explain the meaning of the confidence interval in the context of the problem. The confidence interval, if you remember from the previous lesson that we did on this, is the range of expected values. So what that means in the context of the problem is it is expected that between, I'll do this as percents, 33% and 69% of students drink at least one soda per day. Let me make that smaller so we can kind of fit it somewhere. But that's the conclusion from this. Based on this, if I had to say what the actual percentage was of students that drink soda in the school, it's going to be somewhere between 33% and 69%. Now, that's a pretty large range there. We'll talk later in the problem about what would happen, how to get it not so large of a range. Now, what is your estimate for the proportion of all students who would report that they drink at least one soda per day? So, the mean of the sample is 0.51. So that means out of the people that were asked, the proportion mean was 0.51. So based on that, I would say the answer is approximately 0.51. Whatever I get for my sample approximates the population. So if 51% of the population drank at least one can of soda per day, then approximately 51% of everybody drink at least one can of soda per day. Is it reasonable to say that 40% of students drink at least one soda per day? Well, to answer that, reasonable, plausible, it's the same question. I'm looking at my confidence interval, which was 0.33 to 0.69. So is 40%, is 0.4 inside the confidence interval? Yes. So yes, because 0.4 is in the confidence interval. If instead of taking random samples of 30 students in the high school, the 11th graders randomly selected...
Good morning, sir.
Sorry about that. So instead chose random samples of 60 instead of 30. Well, as I increase the sample size, what happens? Well, the mean, let me just type this, it'll probably be easier and neater. The mean relatively stays the same, and the standard deviation decreases. That's what we talked about before. If I increase the sample size, well, we're still going to have most of the stuff centered around here, but we're not going to have this stuff. We're going to lose this stuff, and the sample distribution is going to come in. The standard deviation decreases, but the mean is still going to relatively stay the same. It's still going to be centered around the same value. So that's what you need to know about sample distributions. As the sample size increases, the mean relatively stays the same while the standard deviation decreases. To find the confidence interval, you do the mean plus or minus 2 times the standard deviation. That gives you the range of expected values. So if it ever asks, well, is this likely? Is this expected? If it's inside the confidence interval, then yes. If it's not inside the confidence interval, no. And the margin of error we talked about for the first time, that's just 2 times the standard deviation. That's how far from the mean it can be and still be expected. And the sample mean approximates the population mean. If out of all the samples, 0.51 was the mean, then that would mean that approximately, if I took a look at every single person in the entire school, it would be approximately 0.51. All right, let's try another one. Number 2. The following is an example of a sampling distribution of heads in 40 flips of a coin. The mean is 0.4955, and the sample in the standard deviation is 0.852. Find the sample standard deviation. Find the margin of error and the confidence interval. So I want you to try that on your own. I'll kind of give you a little bit of a hint to get started. The confidence interval is the mean plus and minus 2 times the standard deviation, and then the margin of error is just 2 times the standard deviation. So please pause, calculate the confidence interval and the margin of error, then unpause. Okay, now that you calculate those on your own, the confidence interval is 0.4955 plus and 0.4955 minus 2 times 0.0852. And I get 0.4955 plus 2 times 0.0852, and then I subtract them. So I got 0.6659, and I've got 0.3251. So it's between 0.3251 and 0.6659. My margin of error is just 2 times 0.0852. The margin of error basically just measures how far I can be from the mean and still be in the confidence interval, still be an expected value. 2 times 0.0852 is 0.1704. Explain the meaning of the confidence interval. Well, the confidence interval is the range of expected values. So the range of expected, let's just say it this way. It is expected that the proportion of heads in 40 flips of a coin will be between 0.3251 and 0.6659. So if I had to guess, and it's sometimes it's easier to think of these as percent, so that's like 32.5% and 66.5%. So if I had to guess what the proportion would be if I flipped a coin 40 times, I'm going to guess it's going to be somewhere between 0.3251 and 0.6659. Anywhere in between there would be an expected value, and it would not be expected that it's not between there. What is the sample mean? What is the population mean? How do they compare? So this one's slightly different than the last question that we did, referring to this, but let's take a look at it. The sample mean is 0.4955. In the last problem, I didn't have the population mean, so I didn't know the actual proportion of students who drank at least one soda per day, but I do know the population mean here. The probability of getting heads is 0.5. The population mean out of 2 possible outcomes, one of them is heads, one of the 2 is 0.5. How do they compare? They are relatively the same. The sample mean and the population mean will be relatively the same. That's the point. The point of doing an experiment, of doing a survey, of doing whatever, your sample mean will approximate your population mean. They are relatively the same. They are approximately the same. I'm going to probably have to transfer my confidence interval here. It was 0.3251 and 0.6659, I believe. Yes. Is the coin fair? Well, we haven't answered this question yet. It's fair. Let me write this down. Let's type it out so it's a little bit neater. Something is fair if the theoretical probability is an expected value. I'm going to kind of throw this at the front of the lesson as well, because this is an important concept. That's not what I just copied. Something is fair if the theoretical probability is an expected value, and by expected value, in the confidence interval. So the theoretical probability of getting heads is 0.5. So is 0.5 inside the confidence interval? Is 0.5 between 0.3251 and 0.6659? Yes, because 0.5, which is the actual probability of getting a heads, is in the confidence interval. Fred flipped a coin 40 times and 65% of the flips came up heads. Is this an expected outcome? Well, is 0.65 inside the confidence interval? Yes, barely, but we don't care if it's barely in or if it's right in the middle of it or if it's right at the edges. If it's inside, it's an expected outcome. If it's not, then it's not. So don't try and use your judgment. There's no judgment here. It's either inside the confidence interval, it's expected, or it's outside, it's not expected. Yes, because 0.65 is in the confidence. And that's it. So what do we do here? The margin of error in confidence interval is just calculating using formulas. Confidence interval is the mean plus and minus 2 times the standard deviation. Margin of error is 2 times the standard deviation. The confidence interval gives you the range of expected values, so it's expected that the proportion of heads in 50 coin flips will be between 0.3251 and 0.6659. So if you flipped a coin 40 times right now, I'm going to expect that you're going to get a proportion that's between those two values. The sample mean is the mean of the sample, which it gave us. The population mean, well, if I'm flipping a coin, 1 out of 2 are heads, so the population mean is 0.5, and the sample mean should be relatively the same as the population mean, approximately the same. The coin is fair if the theoretical probability, in this case 0.5, is in the confidence interval. 0.5 is in the confidence interval, so the coin is fair. And in case you're wondering, what does it mean if the coin is not fair? So a lot of cheaters and gambling, they'll use a coin that's not fair. Maybe it's weighted differently. So it's got the weight on one side of it, so it's more likely to land on one side than the other. That would be an example of a coin that's not fair. And again, to determine if the coin was fair, without doing the chemistry and pulling the coin apart, you would do an experiment like this and see if 0.5 falls in the confidence interval. And finally, if it wants to know if something's an expected outcome, we look to see if it's inside the confidence interval. Even though it's close to being out, it doesn't matter. It's either in or it's out. If it's in, it's expected. If it's not in, then it's not. A class of 28 11th graders wanted to estimate the proportion of all juniors and seniors at their high school with part-time jobs after school. Each 11th grader took a random sample of 30 juniors and seniors and then calculated the proportion with part-time jobs. A dot plot is created. The mean is 0.67. The standard deviation is 0.1. Find the margin of error in the confidence interval. Explain what the confidence interval means in the context of the problem. So we've done this quite a bit now. Why don't you pause and try to do that first question on your phone? Okay, now that you tried it on your own, your confidence interval is the mean plus and minus 2 times the standard deviation. The margin of error is 2 times the standard deviation. So we got 0.67 plus 2 times 0.1, 0.67 minus 2 times 0.1, and we got 2 times 0.1. I don't need a calculator for that one, that's 0.2. And I don't need a calculator for this either. 0.87, 0.47, so 0.47 to 0.87. The meaning in the context of the problem, it's expected that the proportion of juniors and seniors in this high school with part-time jobs is between 0.47 and 0.87. As percents, 47% to 87%. What is your estimate of the proportion of all juniors? Well, what's the mean? If the mean is 0.67, then approximately 0.67, because the sample mean approximates the proportion mean, the population mean. So basically what I got from this question so far is that I'm going to expect that the range, it's going to be somewhere between, it's expected that if I pick someone at random, they're going to be between 47% and 80%, but most likely they're going to be 67 or approximately 67% if I find the average of these students. So basically it's saying that the average is going to be 67%, and that's going to include values that range from 47% to 87%. I'll say that again, what we've talked about so far in the problem. Basically, we're saying that my average is going to be 67%, but it's expected that, that's going to be made up of ones between 47% and 87%. So again, I'm going to probably need my confidence interval, 0.47 to 0.87. Do you think the proportion of all juniors and seniors in the school with part-time jobs will be 0.7? Well, is 0.7 inside the confidence interval? Yes. Is 0.5? Yes. So yes for both, because 0.5 and 0.7 are in the confidence interval. So both 11th graders had taken random sample sizes of 60. How the distribution of sample proportions based on the sample of size 60 compared to the distributions for 30? Well, if I increase the sample size, the mean relatively stays the same, and the standard deviation decreases. So basically what would happen is my mean would stick around 0.67, but my confidence interval would probably get tighter to 0.67. Maybe it would be 0.57 to 0.77. All the values would be closer to the mean. I don't know that for a fact, but in general, it's going to get closer to the mean. It's going to be a smaller range for the confidence interval. That's just me speculating the exact values there, but that's what's going to happen. If I increase the amount of students that I'm asking, my mean is going to relatively stay the same, and the standard deviation or spread or variability or range is going to get smaller. It's going to decrease. I think I'm done with you at this point. I know we did a lot of talking here. I think at this point you should be comfortable enough to do them on your own. So I'm going to call it a day with this. So let's again sum up all the important things that you need to know. I can understand how sample size affects the mean and the standard deviation in the sample distribution by finding the confidence interval. A lot of little things to talk about. So sample size, as I increase sample size, the mean relatively stays the same, and the spread or variability or standard deviation decreases. That's what happens if I go from 5 coin flips to 20. If I go from asking 30 people to 60 people, as I increase sample size, the mean relatively stays the same. The spread, variability, standard deviation decreases. To find the range of expected values, I find the confidence interval. We did this in a previous lesson. The confidence interval is the mean plus and minus 2 times standard deviation. And we also talked about the margin of error, which is just 2 times the standard deviation. The confidence interval is a range of expected values. The margin of error is how far you can be from the mean and be an expected value. The sample mean approximates the population mean. So if 0.51 of my sample drink at least one soda, then approximately 0.51 out of everybody will drink at least one soda. If I want to know if a value is expected or plausible or reasonable, I need to determine if it's inside the confidence interval. And then the last thing we talked about, if I want to know if a coin or a spinner is fair, if the theoretical probability is an expected value, if it's in the confidence interval, then it's fair. If it's not, then it's not. So your classwork/homework is to finish this, and this is going to build into a very, very common 4-point algebra 2 reasons question, which we're going to get to in a couple lessons. But we're going to spend a lot of time. We're going to do one more lesson dealing with more 2-point questions, and then we're going to move on to lessons dealing with 4-point questions. Have a great day.